Welcome to Critical IT Solutions podcast series, where technology leadership meets innovation. Join us as we explore the ideas shaping modern IT, from cybersecurity to quantum computing and everything in between.
A computer solved a problem in 5 minutes, a problem that would take a classical supercomputer longer than the entire age of the universe to crack. Not 1,000 years, not 1,000,000, longer than the universe has existed. That happened in December 2024, and most people scrolled right past it. Today, we're breaking down quantum computing, what it actually is at its core, the jaw-dropping breakthroughs happening right now in 2026, and why this technology is about to reshape cybersecurity, medicine, and modern tech as we know it. By the end of this episode, you'll understand the difference between a qubit and a classical bit, why your encrypted data might already be at risk, and what the so-called transistor moment of our generation actually means. I've got someone here who's been deep in this space, so let's get into it. Walk me through what throw that term around without really knowing what's under the hood.
So the best place to start is with what we already know, classical computers. Every device you use today, your phone, your laptop, any server in the cloud, they all store and process information using bits. A bit is either a 0 or a 1. That's it. An electrical switch that's either off or on. And everything digital, every text, every video, every transaction is just enormous strings of those zeros and ones.
Right, binary. That's the foundation of everything we've built digitally.
Exactly. And for most problems, that works brilliantly. But when you hit certain kinds of problems, simulating molecular structures, optimizing massive supply chains, cracking encryption keys, the number of possible solutions explodes exponentially. Classical computers have to try each solution one at a time, step by step. Even the most powerful supercomputers get completely overwhelmed by what researchers call combinatorial explosions.
So it's not that classical computers are slow, it's that some problems are just structurally too big for them.
Precisely. And that's where quantum computing comes in. Instead of bits, quantum computers use qubits, quantum bits. And here's where it gets genuinely strange. A qubit doesn't have to be just a 0 or a 1. It can exist in what's called a superposition, a state where it's effectively both at the same time until you actually measure it.
Okay, wait, both at the same time? How does that even work? That sounds like something out of a sci-fi movie.
It does, and honestly, the analogy that NIST uses is really helpful here. Imagine a person on a ladder. Depending on which rung they're standing on, they have a certain amount of potential energy. A person can only stand on one rung at a time, that's classical. But a quantum particle, like an atom, can act as though it has two or more distinct amounts of energy at once. It's simultaneously on the lowest and highest rung, and it stays in that mixed state until something in the outside world disturbs or measures it, then it collapses to a single state.
So the act of measuring it forces it to pick a lane.
Exactly. And that's just superposition, one of 3 core quantum phenomena. The second is entanglement. When qubits become entangled, a change to one instantly affects the other, regardless of the distance between them. Einstein famously called it spooky action at a distance. And what that enables is massive parallelism. Quantum systems can explore countless possibilities simultaneously in a way classical computers simply cannot.
That's wild. And there's a third one?
Interference. Quantum computers use interference to amplify the paths that lead to correct answers and cancel out the ones that don't. Together, superposition, entanglement, and interference, these are the ingredients that make quantum algorithms fundamentally different from anything classical computing can do. IBM actually has a great way of framing this. They compare it to photography before and after color film.
Oh, I love that. Tell me more.
So, before color film existed, if you asked a photographer, can you swap the reds and yellows in this image? The question would be completely meaningless. Not because they weren't smart enough, but because the capability to even engage with color didn't exist yet. Once color film was invented, a whole new world of artistic and technical options opened up. IBM's point is that quantum computing is that color film moment for computation. The phenomena were always there in nature, we just recently figured out how to control them.
That's such a clean way to put it. And it also reframes what classical computing even means, like, we only started calling it classical once something else came along.
Right. IBM makes exactly that point. Just like black and white photography only got that name after color film arrived, classical computing only needed a new label once quantum computing entered the picture. It's a naming that happens in retrospect.
And it's worth noting, this field didn't just appear overnight. There's actually a pretty interesting origin story here.
Yeah, quantum computing as a field traces back to the early 1980s. Richard Feynman proposed the idea of using quantum systems to simulate other quantum systems efficiently. And David Deutsch formulated the concept of a universal quantum computer. These were theoretical ideas at the time, but they laid the entire foundation for everything we're seeing today. It took about 4 decades to get from those ideas to actual hardware that can do something meaningful.
4 decades. That's a long runway. So let's talk about what's actually happening right now, because 2024 through 2026 seems like a genuinely different moment. What changed?
So the single most dramatic moment in recent quantum history happened in December 2024. Google unveiled a chip called Willow, and Willow solved a specific computational problem in 5 minutes, a problem that would take a classical supercomputer longer than the age of the universe to complete.
Longer than the age of the universe. I keep coming back to that. It's almost too big to process.
It really is. But what made Willow significant wasn't just the speed, it was what it demonstrated about error correction. One of the central problems in quantum computing has always been that qubits are extraordinarily fragile. They're sensitive to heat, vibration, electromagnetic interference. Basically, anything in the environment can disrupt them and introduce errors. And historically, adding more qubits made the error problem worse, not better.
So more power meant more noise. That's a brutal engineering problem.
Brutal is the right word. But Willow was the first quantum processor to achieve what's called below-threshold error correction, meaning that as you add more qubits, the error rate actually goes down instead of up. According to Forbes, Google showed that increasing the number of qubits actually lowered mistakes, which was a long-standing challenge that many thought was unsolvable. That's a massive deal.
And then Microsoft came in with something completely different, right? Not just better qubits, a different kind of qubit entirely.
In February 2025, Microsoft announced Majorana 1, the world's first quantum chip powered by topological qubits. This is a fundamentally different architecture. It uses something called a topoconductor, which is described as the world's first material that can observe and control Majorana particles. These particles produce qubits that are inherently more stable and scalable. And the design is theoretically scalable to 1 million qubits on a single chip.
1 million qubits on a single chip. That's not an incremental improvement, that's a different category of machine.
It really is. And researchers from the University of Chicago, Stanford, MIT, and several European universities published a paper in the journal Science framing this whole moment in a really striking way. They said quantum technology has reached what they're calling its transistor moment, a critical phase that mirrors the early era of classical computing before the transistor reshaped everything. Functional quantum systems exist, but scaling them into truly powerful machines still requires major advances in engineering and manufacturing.
The transistor moment. So we're not at the finish line, we're at the point where the real race begins.
Exactly. And the paper draws a direct parallel to the 1960s, when early computers faced what engineers called the tyranny of numbers. Adding more components kept making systems harder to control. Quantum computing faces that identical challenge today. The breakthroughs of 2025 and 2026 are the first real signs that engineers are beginning to solve it.
And the money is clearly following the science. What does the investment picture look like?
The numbers are striking. According to research tracking the industry, in just the first 3 quarters of 2025, the quantum computing sector raised nearly $4 billion in investment, triple the total for all of 2024. And Forbes reports that the quantum computing market was valued at $8.6 billion in 2024 and is expected to grow at 32 to 38% annually through 2030.
That's not venture capital dabbling, that's a full-on strategic bet.
And governments are treating it that way too. The US has committed over $1.2 billion to the National Quantum Initiative. Forbes notes that China is apparently investing significantly more in quantum infrastructure and talent. The world has shifted from viewing quantum technology as an academic curiosity to treating it as a strategic requirement for national security, economic competitiveness, and cybersecurity.
Which brings us to the part that I think is the most urgent and the most underappreciated: what quantum computing means for cybersecurity. Because this isn't a future problem, is it?
No, and this is where things get genuinely alarming. The encryption that protects basically everything online, your banking, your messages, government communications, relies on the mathematical difficulty of factoring enormous numbers. Classical computers would take an impractical amount of time to crack it. But a sufficiently powerful quantum computer running something called Shor's algorithm can factor those numbers exponentially faster.
So the entire security infrastructure of the internet is built on a problem that quantum computers are specifically designed to solve.
That's exactly right. RSA 2048, ECC, SHA 256, these are the encryption standards protecting most of the world's sensitive data. According to Geeks for Geeks, quantum computers using Shor's algorithm could break RSA 2048 encryption in minutes. Experts predict this could be possible within the next 5 to 10 years.
And here's the part that really got me when I read about this, the halves now, decrypt later threat. Can you explain that?
So this is the attack that's already happening. Bad actors, state-level adversaries, sophisticated criminal groups are stealing encrypted data right now, today, even though they can't decrypt it yet. They're banking on the fact that in 5 or 10 years, when quantum computers are powerful enough, they'll be able to go back and crack all of that stored data. Your medical records, financial data, classified communications, all of it could be sitting in someone's archive waiting for the right machine.
The attack is happening before the weapon fully exists. That's a genuinely unsettling framing.
It is. And that's why NIST, the National Institute of Standards and Technology, moved so urgently. In August 2024, NIST finalized its first post-quantum cryptography standards. That triggered a global transition to what's called quantum-resistant encryption, cryptographic methods designed to stay secure even against quantum attacks.
So the defense is already being built, but is it moving fast enough?
That's the real question. The transition to post-quantum cryptography is massive. It's not just updating software, it's rethinking the entire architecture of how we secure data. And there's also a flip side to quantum and cybersecurity that's worth mentioning. Quantum key distribution, or QKD, uses quantum mechanics to establish cryptographic keys that are theoretically impossible to eavesdrop on. So quantum isn't just a threat to security, it's also potentially the most powerful security tool we've ever had.
It's both the lock and the lockpick at the same time.
That's a really good way to put it. And that duality is what makes this technology so consequential. It's not just a faster computer, it's a technology that changes the rules of what's possible and what's secure.
I do want to push back a little here, though, because there's a tendency to hype quantum computing as this all-powerful thing that's going to solve everything. But the research suggests it's more nuanced than that, right?
Absolutely. And this is an important counterpoint. A benchmark study from researchers at the University of Stuttgart compared variational quantum algorithms to classical machine learning models across 27 time series prediction tasks. And their results showed that in many cases, quantum models actually struggled to match the accuracy of simple classical counterparts of comparable complexity.
So quantum isn't just universally better at everything.
Not at all. IBM is very clear about this. Quantum computers are expected to be broadly useful for two specific types of tasks: modeling the behavior of physical systems and identifying patterns and structures in information. For everything else, classical computers are still the right tool. The framing of quantum versus classical as a competition actually misses the point. NIST explicitly says the two types of machines will work together, not replace each other.
So it's more like quantum computing is a specialist that gets called in for the hardest problems, not a generalist that takes over.
That's a really accurate way to think about it. And the areas where quantum genuinely shines are enormous in their implications. Drug discovery. Quantum computers could simulate individual molecules with precision that's impossible for classical machines, helping researchers identify pharmaceutical candidates far more efficiently. Materials science, protein folding, financial modeling, supply chain optimization. These are all domains where quantum's specific strengths translate into real-world breakthroughs.
And in 2026, we're also seeing quantum networking start to move out of the lab, right? That's another layer to this.
Yeah, this is one of the developments that doesn't get as much attention, but is really significant. In 2026, quantum networking has seen its first multi-node demonstrations over existing fiber optic infrastructure in real cities. That's not a lab experiment, that's quantum communication happening on the same cables that carry regular internet traffic. It's early, but it's a proof of concept that quantum networks can be built on infrastructure that already exists.
And China is in this race too. It's not just a US and European story.
Very much so. China's University of Science and Technology, USTC, achieved a critical milestone with their Zhuchongji 3.2 processor, reaching below threshold quantum error correction. That's the same threshold Google's Willow hit. Multiple countries are now at the frontier simultaneously, which is why governments are treating this as a strategic priority rather than just a scientific one.
It's a quantum arms race, essentially.
In some ways, yes. And the stakes are high enough that the language of national security keeps coming up in these conversations. Forbes describes national security, economic competitiveness, and cybersecurity as all feeling the impact. This isn't just a tech story, it's a geopolitical one.
There's also something interesting happening with the error correction research surge. The numbers on that are pretty remarkable.
Right. So in 2025 alone, 120 peer-reviewed papers on quantum error correction were published in just the first 10 months. That's compared to 36 for all of 2024. The scientific community essentially tripled its output on the single most critical technical challenge in the field. That kind of acceleration in research is a signal that the field has hit a genuine inflection point.
From 36 papers to 120 in less than a year. That's not gradual progress. That's a field that suddenly believes it's solvable.
Exactly. And there's a term researchers are using to describe where we are now, the fault-tolerant foundation era. It's the phase where adding more qubits actually reduces error rates rather than amplifying noise. That's the threshold that had to be crossed before quantum computing could become genuinely useful at scale, and we've crossed it.
I want to come back to something you said earlier about quantum and AI converging, because that's another dimension to this that feels important.
Yeah, industry experts are increasingly talking about the convergence of AI and quantum as one of the defining trends going forward. Quantum computing could dramatically accelerate machine learning by processing data in ways classical algorithms can't. And on the flip side, AI is already being used to manage quantum error correction, though that introduces its own risks. Research has shown that machine learning-based error correction systems can be vulnerable to what are called physical fault injections, which is a new kind of security concern specific to quantum systems.
So as we solve one problem, new problems emerge. That's kind of the nature of frontier technology.
Always. And that's actually a healthy sign. It means the technology is real enough that people are stress testing it seriously. The challenges that remain are engineering and manufacturing challenges, not fundamental physics challenges. According to that paper in Science, functional quantum systems exist. The question now is how to scale them.
So when you step back from everything we've covered today, the qubits, the breakthroughs, the cybersecurity stakes, the investment surge, what does it all actually add up to?
Here's what I think it adds up to. We are genuinely at an inflection point, not a hype cycle, not a 5 years away promise, but an actual turning point. The transistor moment analogy is apt because it captures both the excitement and the humility of where we are. The transistor didn't immediately give us smartphones. It took decades of engineering. But once it existed, the trajectory was irreversible.
And the implications aren't evenly distributed. Some of this, like the cybersecurity threat, is already affecting people whether they know it or not.
That's the part that matters most for people listening right now. The harsh now decrypt later threat is not theoretical. If you've ever had sensitive data transmitted online, medical records, financial information, private communications, there's a real possibility that data has already been collected by adversaries who are waiting for quantum decryption to become viable. The transition to post-quantum cryptography that NIST triggered in 2024 is the response to that, and it needs to happen faster than most organizations are moving.
And on the positive side, drug discovery, materials science, protein folding, these are areas where quantum could genuinely save lives.
IBM puts it well, quantum mechanics is a bit like the operating system of the universe. A computer that uses quantum mechanical principles has inherent advantages in modeling physical systems. That means researchers looking for new pharmaceutical compounds or engineers designing new materials could get answers in hours that would otherwise take years. The potential to accelerate scientific discovery is enormous.
And none of this means classical computers are going away. That's worth saying clearly.
NIST is explicit about this. Quantum computers will not replace classical computers. The two will work together. Think of it less like a replacement and more like adding a specialist to a team. Your classical computer handles the everyday work. The quantum computer gets called in when the problem is genuinely intractable by any other means.
So the actionable takeaway for someone listening to this, what should they actually be paying attention to or thinking about?
A few things. If you work in any field that handles sensitive data, healthcare, finance, government, legal, the post-quantum cryptography transition is something your organization needs to be actively planning for, not watching from a distance. NIST has already set the standards. The question is whether your systems will be updated before quantum decryption becomes viable. Second, if you're in tech or science, the convergence of quantum and AI is going to create entirely new categories of problems to solve and tools to build. And third, just pay attention. We're living through the transistor moment of a new era of computing. That's worth understanding.
Here's what this really comes down to. We started this episode with a computer solving a problem in 5 minutes that would take longer than the age of the universe. And I think the instinct is to hear that and think it's abstract, it's distant, it's a lab curiosity. But everything we've talked about today says the opposite.
The distance is closing fast. The investment is real. The hardware breakthroughs are real. The cybersecurity implications are already in motion. What's still ahead is the engineering, the scaling, the manufacturing, the integration. But the physics is solved. The question now is execution.
And that 5-minute problem, the one that opened this episode, it's not just a party trick. It's proof that the rules of what's computationally possible have already changed. We're just waiting for the rest of the world to catch up to that fact.